Good evening, everybody. We're going to have a marathon session tonight, I think. We've got a lot of material to cover. This is really going to be the last session before last statistics new material session before the final exam. Next week we'll do a little bit of recap on some things and how you put together a model and take the jump output and build on it. But tonight we're going to cover all of the stuff that you talked about last weekend, multiple regression and in particular categoricals. And those are variables that are not continuous, but in fact have certain discrete states that provide some interesting flavor to our regression models. So we'll do that. We'll spend a fair amount of time on examining categoricals and how they fit into the multiple regression model. And then we'll fill in at the end with a few more questions from the sample final exam number 3. We did some of those 2 weeks ago, and we'll fill in a few more of them. Some of the questions that are based on or centered around categoricals and things like that. So let's go ahead and get started. Just a quick review of some of the things we talked about a few weeks ago. The regression model is based on the true model, where y is a function of some explanatory variables x, x1, x2, x3, and so on. And we can model this with a linear equation with a y-intercept, beta naught, and a coefficient of the explanatory variable x. If you have more than one explanatory variable, you'll have a beta 1, beta 2, beta 3, and so on. And then finally, we've got some error term here, a unique error for each particular example of the explanatory variable. And this essentially encompasses all of the stuff that's left out that we don't have any information on in this regression model. When we actually take real data, a sample, and we build a model from that, you notice we get now into lowercase letters. So y equals b0 plus b1 x1 plus b2 x2, et cetera, until we finally have an error term, which we call a residual term. And this residual term incorporates all of the errors in the true model plus anything that's off because our sample is not quite perfect. So we call this the estimated model. And these errors, of course, are measured from the regression line to each data point. And so it's the vertical distance, that is the distance in the y direction, that a particular sample data point is from the line, either the true line or our sample regression line. A couple of other things people always keep asking about. The simple regression model, and in fact the multiple regression model, has some assumptions about the residuals. And those assumptions allow us to make some statistical conclusions and evaluate the goodness of our model as well. So we need, first of all, for those residuals to be independent. That is, we can't have any kind of a pattern or correspondence from one point to another. The errors should not be influenced by other data points. They should have a mean of 0 and a constant variance. Now the mean 0 is easy to hit because essentially we're building that regression line in order to make those residuals average out to 0. And then they should have constant variance. What does constant variance mean? It means that for any value of x, the variance or spread of those residuals is the same at any point. Obviously, you don't have precise data points. You don't have a lot of them to tell you at any point along x what the what the variance is, but basically you want to make sure that there's no obvious trend or function that varies the distance that these residuals have from the regression line along the line. And we'll see why that's so important for prediction in a minute. And then those residuals should be normal. That is, the data itself should be clustered around or above and below the regression line, and it should take on a normal distribution. So as you can see in the picture here, that yellow line is a representative normal distribution, and all of our points should take on that kind of a distribution in the y-axis. And why is this important? It allows us to do some stuff that we like to do with normal distributions, like confidence intervals and empirical rule and things like that. So if we have a nice normal distribution of data around, above and below the regression line, then we can do a lot of that analysis and figure out goodness of our fit in many ways. Okay, next thing we have to deal with is separating out the model from those errors or from those residuals in order to evaluate how effective our model is. And the relationship here, if we look at the individual y values and subtract the mean of all the y values from that, and then we square that value and add them up, we get something called the sum of the squares for the total data. And that we split into two pieces, sum of squares of the regression and sum of the squares of the errors. And the regression, of course, is how much variation is there between our sample regression model and the average of y. And then the sum of the squared errors is how much is there between our actual data values of y and the predicted value from the model. So those are essentially the residuals that we're talking about. So we're looking at how much variability in the data is explained by the regression line and how much is left over for the residuals. We use this information in a number of different ways, and we'll see it used several times a little bit later. But we can calculate this thing called R squared, which is a scaled measurement of how essentially how much of the variation in y values is explained by the model, by the x variables, and how much is left out. One of the ways that we like to look at regression residuals or errors is we like to look at the RMSE, the root mean squared error. So this is very much like looking at standard deviation. Essentially, it's the standard deviation of those residuals above or below the regression line itself. And so you can see that picture again in the lower right-hand side. Here's how it's calculated. You don't have to worry about that. JMP does all that stuff for you. You realize, of course, that anytime you extract multiple bits of information from a sample, you are taking out some of the information inherent in the sample. So we're dividing not by n, but by some reduced value of n. It depends in a multiple regression model, how many variables are you trying to model? So this should all be pretty much easy stuff. You remember it and you kind of know how to apply it and know what it means, that sort of thing. A little bit later tonight, we'll get into the JMP output, and you'll see this stuff showing up, and that might be very useful on the final exam, just kind of being able to look at that data and figure out what's going on with your data and with your model. One of the things that we think is pretty important about the SRM and the MRM assumptions is this constant variance, so much so that we have this fancy name for it. Constant variance along the x-axis, or the y-axis for that matter, but along the x-axis is what we normally think of it, is called homoscedasticity. Lovely word. And if we have a non-constant variance, it's called heteroscedasticity. And as you can see in the picture, we expect at any point along the x-axis, we expect the residuals, the errors, or the distances from data points above and below the regression line to take on a normal distribution. And we can use that to do things like prediction intervals and empirical rule applies and all that sort of stuff. The problem is if the data doesn't behave according to our assumption, and our assumption is that the standard deviation of that normal distribution is the same at any point along the x-axis. If we don't have that, then we have some difficulty when we try to apply empirical rule to the data as a whole. So you can see here in this picture, I've got a case where the data is expanding farther and farther away from that regression line as we get further and further to the right on the x-axis. And I kind of drew in an approximate normal distribution in red for small values of x and in yellow for larger values of x. And you can see the standard deviation of this normal distribution is larger to the right than it is to the left. Heteroscedasticity, it's a problem that you want to check when you look at your data. And why is that so important? Well, one of the first reasons why it's so important is if we want to use this model for doing predictions. And if we want to use the model for doing predictions, we do, ooh, where's my pen? My pen is weird. Okay, let's try this. Much better. Prediction intervals. If we're going to use this model in order to predict values of y for new values of x that come along, in other words, we have a set of data we've gathered and we want to use that in order to figure out what might happen if we have a new case or a new data point showing up. What would the y value that corresponds to the new x value that we have, what would that y value be? What would we guess or predict that it would be? No guesses here, I guess. So essentially, since we know the distribution of the errors above and below this regression line, and we assume that it's in a normal distribution, we can make some statistical measures of how far from that regression line our prediction could be. And so what we're going to do is to figure out what our prediction interval is, that is the range above and below the regression line where a new value of y could be. We're going to put together an error band around the regression line, as you can see in the picture, in the dotted red lines. And this line is basically sort of a confidence interval for our prediction for any new value of y, new value of x that we come up with. And we're going to calculate it using the regression line. That's our predicted value. But then we realize that the actual value that corresponds to a new value of x could be a little bit above or a little bit below, and we can estimate how far that's going to be by adding or subtracting 2 times the root mean square error, and that will give us a 95% prediction interval. So we're just applying the empirical rule to the normal distribution of data points which are normally distributed above and below that regression line. And so when we come up with a new value of x, let's call it x star, our prediction model, our regression model, allows us to predict some value of y here, but we know a real value, and if we actually had a real data point there, it could be anywhere in that range in this prediction interval plus or minus 2 RMSE above or below y star. So this is, in the picture here, we have the possible range of y values. And so basically this is the range of uncertainty about the prediction. So we can say if we have a new value of x that we want to predict the corresponding y for, we plug it into our regression model, come up with a value of y, and we can say that with 95% confidence, the true value of y will be within this range of the predicted value plus or minus 2 RMSE. So if we were to look at this in JUMP, they will give us a dotted line, and in fact, it's really a curve because, as you realize in JUMP, they're really precise about calculating confidence intervals, and so you probably will see a little bit of a curvature to that interval because as you get further away from the center of the data, you can be a little bit less confident about it. But this red dotted line here gives us a really good measure of the goodness of our model for prediction, and that line is y plus 2 RMSE, and the line below is minus 2 RMSE. And if you were to look at it along the regression line, you would see a normal distribution of possibilities, where this is the regression line, and our possible range of values is plus 2 RMSE above that and minus 2 RMSE below that. And as you can see, that's why we need to have a constant variance no matter where you're looking along the x-axis. Otherwise, we can't use that empirical rule and apply one prediction interval for the whole model. Let's see. One other thing I wanted to talk about here, but I can't remember what it was. Oh well, we'll get to it. I know we'll come to it later tonight. And so we call this a prediction interval because it's useful if we are trying to use this tool for prediction. But the other thing that we're concerned about, not just how accurate is our prediction using the model, but how good is our model? How much can we rely on the values that we have derived from the sample data that we have? And this is where something called the confidence interval comes in. And we'll call it the confidence interval of the slope. So when we build this model, we have sample data. We know that a sample is a subset of the entire world of data. And so we know our model is going to be approximate. It's going to be an estimate of what the true relationship is. And so just like we dealt with hypothesis testing of the mean, for example, of a set of data in the first half of the class, here we want to know how good are the values, the coefficients, and the y-intercept that we've derived from this sample data. If we come up with an intercept of 2, could it really be 2.1 or 1.8 or something like that? And what about the slope? That is the coefficient of any of the x variables. If we have a model that says y equals 2 plus 13x1 minus 7x2, how confident are we in the value of 13 for x1 and minus 7 for x2? What if it's minus 8? What if it's minus 7.3? How do we have a way of measuring how close our model is to what would be the true model using all of the population? So this is not really talking about the errors, that is the part of the variation in y that's not explained by the model, but we're talking about the validity of the model itself. How good is that estimate of all those coefficients of the x or explanatory variables? Again, looking at the idea of hypothesis testing and all that sort of stuff, you'd recognize the language. Basically, the confidence interval is the range of slope values where we're confident to some level, confidence level, that the true slope lies. And the idea, of course, is it's going to be plus or minus 2 standard errors of the coefficient. So B1, for example. So if our true model, capital Y, equals beta 0 plus beta 1 times x1, and our estimated model that we have derived from the sample data we have is y equals b0 plus b1 times x1, how close is b1 to beta 1? And so we need to come up with a way to measure this standard error, right? Remember, if we were just looking at a set of data and we're looking at the mean, we figured out that the standard error was dependent upon the standard deviation of the underlying data, the sample data, and the size of the sample. The more data points, observations in our sample, the better our estimate of that mean value would be, the closer our sample mean would be to the true population mean. So we had this 1 over square root of n factor in there. We have a similar thing going on for the standard error of the slope. And every time Microsoft updates either Windows or PowerPoint, they blow away all my pens, so I have to rebuild the whole thing. Thank you, Microsoft. Anyway, standard error of the slope. Do we have any people from Microsoft this year? I don't remember. So it looks a lot like a normal standard error calculation. We need the standard deviation of the variation of the data points around our regression model. And we That we know, that's the RMSE. That's the variation above and below the model that our data tells us. And we'll divide by the square root of n, the number of observations in our sample. But we have one other thing that we need to deal with, and that is the spread of x. If we're going to look and try to estimate the slope of a line that covers our data, the central part of our data, if we have data points that are really far apart, we've got basically a good foundation to figure out the angle or slope of that line. If we're trying to make a calculation of what the slope is based on a narrow range of data in the x direction, then we're going to have a higher probability of error. In other words, we're going to have a larger error if we have only a small range of x values to deal with. And so what happens is we have an additional factor, and that's 1 over Sx, where of course you recognize that as the standard deviation of the x values in our sample. So if our x's are spread far out, our slope estimate is going to be a little bit more accurate than if our x values are very close together. So it's that kind of the balance idea. So if we were to look, let's take a look at the picture. We've got x, we've got y. We have an intercept here, b0. We have our regression line. Y equals b0 plus b1x. That's the green line here. And if we were to look at the range of possible slope values that we could take on, knowing that we're not going to have perfect, exact, equal to the true slope, we'll have this range of different slopes, and we can look at that as the confidence interval of the slope. So if the slope, say that green line is slope is 1/2, we have some kind of a confidence interval, we could say with some level of confidence, like 95%, using 2 standard errors. We could say that the slope could be a little bit more than 1/2, say instead of 0.5, 0.52, down to as low as 0.48. That would be the confidence interval that we would have for that value of the estimated slope for our model. So that's pretty straightforward. You might see questions on the final exam, for example, that talk about the confidence interval for the slope. You might find questions that ask you about what would happen if you let's take a good example. If you were to take an outlier in X out, and suddenly the data you have is a very small range, then it's going to impact that confidence interval. Now you have to judge whether or not that outlier actually adds anything to your model, and if it does, maybe it's a false reduction in that confidence interval. You have to use a little bit of insight and intelligence to evaluate that. Notice again that we're using RMSE, and that an assumption here that we don't talk about that much is that the variance or the standard deviation of RMSE is the same at any point along the line. Otherwise, we don't have a really good confidence interval for the slope. Maybe it's different at different points along the line, and that's kind of hard to imagine for a linear model. So if we're violating that homoscedasticity assumption, then our confidence interval is going to look a little bit weird. So anyway, that'll be a very important thing when we look at particular models to determine whether or not that model has any power to it. Is it a usable, worthwhile model? And the main thing that we're going to deal with is that slope significantly different than zero? Because if it isn't, if it could possibly be zero, if zero lies within our confidence interval of that slope, and we couldn't reject the idea, the null hypothesis, that the slope could be zero, was zero, then the model has no use for us, because if the coefficient of one of the x variables is zero, then that x variable contributes absolutely nothing to the value of y. So we have to be very sure that we test each of these slopes to make sure that they do have some contribution, that is, the slope is not zero, that we have that the x variable has some contribution to explaining the corresponding y value. We can do the same thing for the intercept. And it's a little bit more complicated calculation. You can probably look it up in the book and see that we're often not so much worried about the intercept because we can't really do a good hypothesis test on that, because we don't have a good null. In other words, we can't say, could the intercept possibly be zero? And if it is, then should we reject this intercept value? No, because intercept could be zero in real life, could be positive, could be negative. So there's no particular value that we would want to reject in order to tell us whether that intercept value was a valid, useful number or not. Sometimes we just have to live with it. Okay, so those are the key things that are going to be impacted by those assumptions about a simple regression model or a multiple regression model, and particularly the assumptions about the distribution of the residuals around the regression line. Let's go ahead and take a look at some of the jump output that tells us a lot about this, about these ideas and these difficulties we might encounter. So here's what you might see as the first part of a jump regression model. And this tells a lot of stuff. This one comes from, I think this was actually from sample exam number 3, so you've probably seen this already. The first part, summary of fit. What is it telling us here? We've got a couple things going on. R squared, that's the first value we have. And remember that R squared is calculated as the ratio of the sum of the squared residual, the sum of the squared regression values divided by the total sum of the squares of the differences between y values in our data and the average y value. So this is because we're dividing by the sum of the squared total, it means that R squared is scaled, and because they are squares, it will always be positive, and so it's scaled between 0 and 1. So essentially what we find here is that in this model, these x values and this model is explaining 0.849445 of the variability of the data in y. We'll call it about 85%. So 85% of the variability, the variation in y, is explained by this model. 85%, by the way, is really good. It's pretty high. It says there are additional things that might be influencing the y values for any particular x value. We throw those all into that error term, but we can say that the model itself is telling us about 85% of that variation in y, and the error the errors are kind of including 15% of that variability. Now we have this thing everybody keeps asking about it, R squared adjusted. Well, R squared adjusted is compensating for the fact that we are we're trying to extract a lot of information from this set of data, and as we add more and more variables that we're trying to extract from the data, the coefficients of each x variable, the R squared gives us a little bit of an exaggerated uh, evaluation of the effectiveness or the usefulness of this model. So there's a way of adjusting it to kind of take into account the fact that you've pulled out some degrees of freedom, you've used up some of the information that's inherent in that sample data, and you don't really need to know anything about this. It's not going to be in the final exam. I'm 99% confident. But if you want to look at it, R squared adjusted is calculated as 1 minus R squared times n minus 1 over n minus k minus 1. So if you look at that and you can kind of pull it apart in pieces and figure out what's going on there. Basically, it's reducing R squared a little bit to take into account the amount of information you're extracting from that sample data. So in this case, it's we've only got a couple of variables. Although when you look at it, we have a entity type that introduces more variables into it. We'll look at that in just a minute. But our R squared adjusted is only a little bit less than the full R squared. The next thing we have here is root mean squared error, 10,212. And of course, that is RMSE. That's the key standard deviation of the residuals that we'll use in confidence intervals, prediction intervals, and so on. So standard deviation of the residuals. And then the mean of response. What's the response? Well, the response is just the Y value. And the mean is Y bar. It's the average of all of the Y values in our sample data. And of course, remember that we use that average to calculate some of the squared total, some of the squared regression, some of the squared errors, etc. Then finally, we've got the observations or sum weights, and that's 2805, and this is just n. How many observations within our sample? So that's the top first table in our jump output. The next one is analysis of variance. It tells us a little bit about the sum of the squared residual. In some circles, SSR is sum of the squared residuals, which is actually SSE, so it can be confusing. Anyway, sum of the squared regression and sum of the squared errors, and these things should add up to the sum of the squared total. So the first line we have talks about the model itself, and then the next line is the error contribution, and then finally the bottom line will be the total. So we can take these things and add them up. Skipping over 2 columns, we have the column called sum of squares. Well, that's SSR, SSE, and SST. And if we take them and add the first 2 lines up, we should get the bottom line. And you can go ahead and plug those into your calculator. It should come out exactly right. On the left, the second column, we have something called DF, degrees of freedom. And again, this is the number of degrees of freedom that are pulled out of our data sample, reducing the 2805 um, to an effective lower value. And for this particular model, we have a continuous variable, monthly revenues, and we have a business entity type that has what is it? Three different possibilities. So we have a bunch of values, coefficients that we're pulling out. And so that pulls out 7 degrees of freedom from our sample, and we effectively are reducing the accuracy of our. That's probably a poor way of putting it, but the the goodness of our model by a little bit. And if we look at it, we'll find that the degrees of freedom that are devoted from the model, subtracted from the total number of observations, less 1, because we've already pulled out the average value of y, that gives us the degrees of freedom that are assigned to the error. So again, we can add those things up. But more importantly, when we calculate the mean of the sum of squares, we're going to use those degrees of freedom as part of that denominator. So the next column over takes the sum of squares and calculates the mean of those sum of squares, which is kind of nice. So we're looking at sum of squares divided by degrees of freedom. And that allows us to look at F ratios. So this is also what we would call the whole F statistic. And so it's essentially this F value, in case you ever wondered where it came from, it's not a count of standard errors like T is. It is essentially the ratio of the mean sum, mean sum of the squares of the model divided by the mean sum of the mean of the squared sum of the errors. And this is essentially telling us the ratio of how much the model is telling us, how much the regression model is telling us compared with the amount of errors or residuals that are left over. And if our model is not telling us a lot, then that F statistic should be low. And if it's telling us a lot, the F statistic should be pretty high. And essentially what it's doing is it's giving us a measure of the significance of the model as a whole. And just why is it called an F statistic? It's based on an F distribution, and we won't go into what an F distribution is. Just think of it, realize we're doing it when we do a t-stat. It's not quite a normal distribution. It's a student's t distribution. It's a kind of modified normal. An F distribution is a little bit different. It's not fully symmetric. Again, you can go into the textbook if you really want to dive into this stuff over your Christmas vacation, holiday vacation, for example. Anyway, so the idea here is that we can use this F ratio much in the same way that we use a t statistic to evaluate the goodness or the validity of this model. But in this case, it's not a t statistic for a single value like a coefficient giving us a confidence interval. It's a evaluation of the whole model itself. So if this t ratio if this F ratio is fairly high, then we know that the model itself is significant. And if it's low, then we know that the model is probably not reliably significant. And normally we look at, especially for single um, regression models, the F ratio of 4 or more, because essentially when you just have one X variable, F is approximately equal to T squared. So we're looking for a T value of 2 or more. We'd be looking for a value for F of 4 or more. But more importantly, and the way we really want to look at this, is this probability number. And that probability is much like the p-value on a T statistic. We're looking at, in order to judge the significance of this model as a whole, we're going to look at the p-value of the F statistic. And again, we're going to be looking at, for a 95% confidence in this model, we're going to be looking at a 0.05 or less. And if it's greater than 0.05, then we don't have a lot of confidence in this particular model, including all of the variables, all of the explanatory variables. So, question that you might ask is, if we took and did a t-test on each of the slopes of the model for all of the x variables in the model, and they all came in less than 2, meaning that we can't reliably say that any of the slopes are different from 0, can we get an F test or an F ratio that indicates that the model is significant? And the answer is yes, we can, even if it looks like none of the individual coefficients are by themselves significant. Sometimes you can combine, the combination of multiple explanatory variables is enough to bring the model as a whole into reasonable significance. So it is possible that you could have none of the coefficients of the x variables individually being significant, but as a whole, when you put them all together, you could have a significant model. So that's the analysis of variance, very key set of information. The next one is the effects test. Now we're going to look at each of the estimates, the estimates of the coefficients and the intercept. And for the effect test, we're here looking just at the coefficients. So what are we doing here? Well, we can do a similar kind of F ratio on each of the individual coefficients, and we call this a partial F test. And I won't go into the calculation of that. You can again look that up. You won't need it for the final. JMP does it for you. But if you look at the rows here, we have 3 different rows. The first one is called monthly revenues. I think in this model it's monthly revenues for the various businesses that are being examined here. And then we have the next line is something called the business entity type. And this is a categorical variable that has, I believe it's 4 different types: sole proprietorship, C Corp, LLC, I forget what the other one was. So it's a categorical variable. It takes on specific states. And then we have the third line is an interaction term. We'll get to talking about those in a minute. But this interaction is between the type of business we have and the monthly revenues of that business. So again, we're going to calculate the sum of squares value for each of these individual coefficients, and we can calculate from that an F ratio, a partial F test. It's essentially an F statistic for each individual estimated coefficient. And this is like I said, I won't go into the way it's calculated specifically, but basically what we're doing is we're taking the whole model and then pulling out each of these variables in turn and evaluating whether the model is significant or not. And by pulling out each of the ones in turn, we'll come up with what we call a partial F test that tells us about the significance of the contribution of each individual coefficient, each individual X variable. And again, same thing here. We're going to use the p-value to determine significance. And we can do a t-ratio or t-test for each of these variables, but you're going to see, I think in the next slide, why that's sometimes troublesome, sometimes not very good. So the partial F covers one variable, but in the case of a categorical, that also means that it encompasses all states of a categorical variable. So anything else we can come up with here? Any questions on these tables? I know we've gone through a lot of this information before, and I think by now most people should be getting a bit comfortable with it. Any questions on any of the information that we have here? Okay, well, finally we get to the core of our model. And in this case, we have what are called expanded estimates. Notice in the effect test here, we had a categorical variable called business entity type, and it was a single line. But what we really have to do, and what JMP does when we have a categorical variable, it kind of splits it out into multiple X variables. So there's an X variable for one state. In this case, it's corporation. There's an X variable for limited liability company. There's an X variable for a partnership and an X variable for sole proprietorship. And so it pulls out all the values, individual values of a categorical variable and splits them into additional terms or separate terms. And that's why we call this table of expanded estimates. It's taken each of the categoricals and expanded it out to show us the effect of each individual level. So what do we have here? So the first column, tabled term, or entitled term, is talking about all of the variable coefficients, the variables, the X variables, and the y-intercept. And so the intercept, of course, is what we would call the B0 value. The monthly revenues is our first X variable. So the estimate for monthly revenues is B1. And then we've got 4 rows here that constitute the categorical B2. And then finally, we have this interaction. We'll talk more about that in a minute. And this is basically a B3, and it's an interaction between X1 and X2, the monthly revenues and the business entity. So here are our estimates. We have a number. These are B0, B1, etc. And so the intercept here is 3850, and so we build our model y equals 3850 plus The next one is the coefficient of monthly revenues, 0.76 times monthly revenues, and so on. The categoricals, now that we have it split out, essentially there's a B21, a B22, a B23, and a B24 here, and depending upon which level or which value of the categorical variable we have for any particular observation, we would use one of those estimate coefficients or one of those coefficients for the categorical in order to figure out what the contribution of that level of categorical would be to the Y value. Now, we have a column standard error. Again, you're familiar with this, just like you would have in a single regression model. This is the standard error of the coefficient. And from that, we can calculate the number of standard errors away from zero. And that gives us a t ratio. So it's a t-test statistic in the next column. And if you look at that, you can calculate them out yourself. How many standard errors is this estimated value from zero, and that will give you the t ratio. And of course, the probability is the probability of getting this value if the actual value was zero. So probability of, come on, pen, getting something at this value or more, this value 11 standard errors or more away from zero if this in fact was, if the null could be correct. So again, you're going to be looking for a probability of less than 0.05 for a 95% confidence in your coefficient here. So these four are combined. They are the categorical variable that we are dealing here with, business entity type. And then we have interaction terms, which also have those four different levels of the categorical. And we'll put those together. In fact, next week we'll put together a whole huge model and show how all of these numbers get combined in order to allow us to build a model and then use that model. Notice in this case that let's take the categorical variable itself. Notice for each level there's a different t ratio. So for each of these estimated coefficients, for each of the levels of the categorical, we have different values of the t-test statistic. And some of them look like they're significant and some of them don't. So are we to conclude that this model is significant only for corporations and partnerships and sole proprietorships, but not for partnerships? No, that's an incorrect interpretation of this. If you want to look at the value of that or significance of that particular variable, you have to go back here to the F ratio that looks at collectively all of the different levels of that categorical variable and tells us the t ratio is 3.8199 and the p value is 0.0096, which says that overall that categorical variable is a significant contribution to the model. So be careful when you look at the t ratio or the t-stat for categoricals. What else do we have here? Just to be complete, we have a continuous variable. One that can take on any real value, and we call that variable was called monthly revs. And then we have a categorical. Business entity type. And that business entity type has 4 possible states. C, LLC, P, and SP. And so for each, we can take on a value of true or false. And of course, they are mutually exclusive. So only one of them can have a value of 1 or a true value out of the group. So if you take any particular data observation from your sample and you look at it, that particular company can only be a corporation or an LLC or a partnership or a sole proprietorship, but it can't be more than one of those things. It can't be a partnership and a C corp at the same time. So only one of those can be true. And so you can see when you build a model, only one of those estimates comes into account for any particular type of business. Now, something to remember when you're building the model, when you're putting the model together and trying to, say, predict the value of Y, in a case where the categorical has more than 2 possible states, we have true, that is, if that state is the active state for that particular data observation, true is 1 and false is 0. But if we have a categorical with only 2 levels, it's a little different story in JMP. So for example, gender, male or female, if we get into the multiple levels there, I'm not going to go there, but let's say we have some kind of a categorical that only has 2 states. And so the value there that each one takes on is either +1 or -1. A little bit different. So when you're interpreting your models and trying to use them, doing calculations with them, keep that in mind. Okay, so this is all the information that JMP is giving us. It's a lot of important stuff. We got R squared. We have adjusted R squared if that's important to us. We've got these standard errors and RMSE and things like that all pre-calculated for us, which is very useful if we understand where they came from. We've got our F tests for the model as a whole, and we have partial F tests for each of the variables, including the categoricals. And then finally, we break it down even further. And this is where you would actually construct your model from this table. And we have t-stats for each of the continuous variables, the intercept, and the individual levels of the categorical variables, and in fact, the interaction terms with the categoricals as well. So if we were to look at the continuous variable only, we would have a model that looked like this: y equals b0 plus b1 x1. And so we would get, in this case, it's called size is our y, and the size would be 3850, that's our intercept, plus 0.76 times the monthly revenues, or mothly revenues. And that's what our model would look like. And of course, we would have a slope of 0.76. X would be monthly revenues. And the Y is a measure of the size, and this intercept would be at 3850, B0. That's what the model would look like without the categoricals. Very straightforward, single regression model idea. Shouldn't be any surprise to anybody. Now, let's add the categoricals. And so this green line is the same one we had in the previous slide. That tells us about the intercept and the slope of the monthly revenues, the continuous variable. If we had more than one continuous variable, we would still have a regression line that would have values for all our slopes for each of the continuous x variables. But here we only have one. So let's look at this green line is the regression without categoricals. So ignoring them. Now let's add the categoricals. So we'll do that, and our model will start to look like this. Excuse me. Y equals B0 plus B1 times X1, which is our continuous variable, and then we have a B2 times X2. This is the categorical term. And B2 really is split into 4 possible values, one for each of the states of the categorical. So we've got 4 terms, subterms. They could be C, LLC, P, or SP. And each one of these terms could be 1 or 0. Mutually exclusive. And I hope I'm not presenting this in a way that's more confusing than clarifying. But because what happens is we end up expanding this out so that the model looks like this. B0 plus B1 X1 plus now we're going to split B2 into these 4 different cases. So B2 for a C Corp times the value of the variable C plus B2 LLL for the limited liability corporation plus B2P for the partnership plus B2S for the sole proprietorship. So now you can see what goes on here. If you were to take any particular data observation, we could take the intercept, add to it the slope of the monthly revenues, X1 times X1, plus one of these subterms. So if it was an LLC, the value of LLC would be 1, and we would add to this model the value of the estimate for what was it, LLC, which is 289.78. And so that's how we would figure out what the Y value should be based on that categorical. So essentially what we have is Y equals 3850 plus 0.76 times monthly revenues, or monthly revs, plus one of these cases. So either minus 1007 times C or plus 2028P or minus 1310 SP, or for the case that we were talking about, plus 290 times LLC. So pick one. One of those categories of the categorical variable will have a value of 1, the others will have a value of 0 and will not contribute anything to our y value. That's how it gets put together. Now, if you were to look at this, what's the graph look like for this? So if we were to take, for example, if a particular observation was for a partnership, we would add 2028 to the overall model that incorporated intercept and the continuous variables. So we'll take that green regression line and we'll basically add a constant 2028 to that for a partnership, and essentially we're shifting that up, whereas the intercept here was 3850 for the plain regression without categoricals. Now for a partnership, we add 2028 to that, and the new intercept is 5878. And in fact, we've added 2028 to y for any x value. And so essentially we created a parallel regression line for a partnership. Let's take a look at LLCs. For an LLC, we add 280. And so we're going to shift that regression line up to the yellow line. If we have a C Corp, we have a negative contribution, minus 1007, and we'll shift it down for a C Corp. And finally, for a sole proprietorship, we'll shift it down by 1310, and that comes down to the bottom red line. So essentially, every time when we put in a categorical variable, we're doing a parallel shift of the basic regression without the categorical. So each categorical will add or subtract a constant value to the initial regression line, the bare regression that we started with. And so we can also think of these as parallel regressions. And so that's what a categorical does for you. It adds a constant value to your y, depending upon what level or what state that categorical variable takes on. Okay, so that's pretty simple, pretty straightforward, and you can build your model, mathematical model, and make predictions of y and that sort of thing at any point. But then we've got this other thing called an interaction categorical. And we also sometimes call that a slope categorical. And this is the other term. Let's look at it here. Down at the bottom here, you can see the bottom row here is called monthly revenues times business entity type. So it's the interaction of the categorical with the effect of the monthly revenue continuous variable. And because we're multiplying those together, it is not shifting the regression line, but changing the slope based on monthly revenues. So for each particular level of the categorical, the effect of the monthly revenues, X, is different. So if for example, we have a C Corp, magnify the effect of monthly revenues on the Y output. And what we get here is, for example, Y is equal to B0 plus B1 X1. That's our continuous part. And then we'll add a categorical interaction where we take x1, the continuous variable, and multiply it by the value of the categorical, and then apply a value, a coefficient to that. And what we're looking at is if we take the basic model, the green line here, 3850, intercept plus 0.76 times monthly revenues, and then we'll add to that model one of these interaction terms. So in this case, it's 0.115 times C times revenues, or 0.023 times LLC times the revenues, or minus 0.164 times P times the monthly revenues, or 0.026 times SP times the revenues. So what does this do? It's essentially pick one of those. If your data observations happens to be an LLC, you will add a term of 0.023 times the revenues. And so essentially this is, the model becomes, for example, if it's an LLC, plus 0.76 times monthly revenues, plus an additional 0.023 times monthly revenues. And that actually can be summed up as 0.783. And so now, instead of a slope of 0.76, we have a slope of 0.78. And so the slope is increased. So our regression line now rotates up or down depending upon which way we're going. In this particular case, I haven't drawn the picture quite right, but let's say this top red line might be the slope of our regression if we had a C corp. And we would, with this interaction term, we would rotate that line up, increase the slope of the model. A lot of people have difficulty with this, but if you look at it, hopefully look at it as you're going to add or subtract something to the initial slope of that continuous variable based on the interaction of each level of the categorical variable. Now, finally, we add them all together. We've got the intercept or parallel contribution of the categorical variable itself, plus the slope change for the interaction terms. And now you can see that we're going to add both of these effects, shifting the regression line and changing the slope of the regression line. So for example, if we start with the green regression line and we have an LLC, we will shift it up essentially by the amount at the y-axis, and we will rotate it, that is, change the slope as well. So we'll start with the base model. We'll add the intercept effect. or the parallel shift, then add the cross-term slope for each case. And so you can see all the possible contributions here. We have some that go down. They get rotated either higher slope or lower slope, like the upper one. And then we have two contributions of each level of the categorical, either as a shift of the line or as a rotation of the line. Yeah, might as well put it out. So y in this case is 3850. That's the initial intercept, plus 0.76 times monthly revs. That's our base. And then for the intercept, the plane intercept, or just the categorical effect, we will have minus 1007 times C, or plus 290 LLC, or plus 2028 P, or minus 131 SP. This is our intercept contribution of the categorical. It's shifting that y-intercept up or down. And then we have the cross or slope or interaction terms plus 0.115 times C times monthly revenues, or plus 0.023 times LLC times monthly revenues. And so C and LLC are 1 or 0. So you're either adding or not adding. 0.164 times partnership times monthly revenues. And then finally, the fourth state 026, sole proprietorship times monthly revenues. And just to be clear here, well, I'll call it MR in all places. And these four terms are the cross terms, or what we call the slope terms, or the interaction terms. Okay, we've got everything for categoricals. The plain vanilla categoricals that shift the base regression line up or down in a parallel fashion. We have the cross or interaction terms, which change the slope of a particular continuous variable. And of course, we can have both. And in fact, if you have a model that has cross or interaction terms, you need to have the plain categorical variable in there as well. So you can't put the model together that has just the interaction terms. Now, used to be this was an option that you had to select, but I think now JMP takes on a centered interaction as a default. You can ask it to do it differently. So by default, it will center your interactions. So our interaction terms look like this. We change the slope, but when you center them, the rotation of the regression line is in the middle of the regression line as opposed to starting at the y-axis. So this one would be not centered, and this would be a centered. So you can see if you're centering it and you have an interaction term effect, it's also going to deal with a shift up or down of the y-intercept. It gets it kind of complicated, but you'll see this frequently, and you're going to see it here. So it centers the term around x bar, the mean of x, the middle of x. So for example, one of the problems in sample exam 3 has something called store type. And one of the cases is local. And you would multiply that by the continuous variable, which in this case is a transformed, log transformed version of customers. And then you see this extra thing, minus 8.33. And then finally you have the estimated coefficient, 0.1086. So this is the variable store type times log of customers, and this is the estimated coefficient, what you find in the table. And so the impact is that this minus 0.833 also shifts the line up or down. In this case, it shifts it down. And so it affects the regression. If for example, local is equal to 1, we now have a model that looks like this, 1086 times 1, which is store type local, times log of customers minus 8.33. And so that works out to be minus 0.9046, which is the intercept, plus the slope term, 0.1086 times the log of customers. So we have impacted the intercept as well as the slope. And so that's what we've done here. Okay. So when you see that kind of complex variable name, that's what's going on. It's centered the interaction term such that you actually shift it up or down as well, so that you're not rotating the slope of that regression line around the x equals 0 point, but you're doing it around the middle of the x data. Let's see. If you have, this is a non-centered case, if you have a categorical with two states, this is just something to remember. You can do this with a centered case as well, but this example, we have one categorical with two states. Jump likes to treat them as a value of +1 or -1. And so we would take the base this would be the base, and we would shift it up +1 or down by -1, and then rotate it. So for example, we're going to shift up by +1, and then we'll rotate it with, in this case, a negative. And if we had a minus, if we had the other state of the categorical, we would be shifting it down. Okay, any questions on that stuff? A few more things we want to cover. Let's talk briefly about partial and marginal slopes. This is often kind of confusing. Put some information on your cheat sheet to remind yourself. A partial, what am I doing here? the partial slope, think of it this way. It's talking about the direct effect of a particular x variable on your response, your y, and it is essentially the change in response, the y effect, for one predictor in a multiple regression model, one predictor variable, one x variable, taking the others into account. So this is essentially what you do when you do a multiple regression model. You're pulling apart the effect or the impact of the predictor variables, the x values, um, so that you can tell the effect of each individual value, the direct effect of each individual value, without at the same time confusing it with the impact of other variables as well. If you were to take and do a single regression model on that x variable, you would be finding a marginal slope because you would be ignoring the other variables, and you would end up getting the direct plus the indirect effect, where the slope is calculated based on one variable, ignoring the others. So if you were to take a set of data, a sample, that where the y value, the response, was affected by more than one input, essentially more than one x variable, and you did a single regression model ignoring all but one of the x variables. What you would end up with is a model that not only had the effect of that one x variable, but indirectly it would have the influence of all the others thrown into that one coefficient. Because you can't just ignore the impact that those other variables have. If you're to do a multiple regression model, essentially what that model does is it pulls out the impact of those x variables individually and assigns some influence or coefficient to each one of those. And so now you have the individual contributions, the direct contributions of each of those predictor x variables to your model. And just to complete that thought, partial is what you get with a multiple regression. And a marginal is what you get when it's taken as a single regression model. I'm sure you're going to have at least one question on the final that asks something about partial versus marginal slope. Okay, I should also mention that when you're doing a t-test in a multiple regression model, you are essentially testing for a non-zero slope after taking into account the other variables. So we're pulling out the significance of a single variable in a multiple regression model. Remember the R squared thing. A key thing to remember, and I think few people forget this, is if you add a new variable into a multiple regression model, you will increase R2. R squared. And R squared is a measure of explanatory power. How good is your model at explaining the variation in Y? But when we look at this, you look at it and you see, you put together a model, say in your homework, and you've got a whole bunch of possible X variables. And you put together a model and you have an R squared of 0.3. And then you add in another variable and you get an R squared of 0.33. Is that a big impact or a small impact? Is it a big increase in power or a not so big increase in power? So when you're evaluating whether this variable has added to your model and is useful in your model, it's best to look not at R squared, but 1 minus R squared. And that number is the unexplained stuff. And I'll explain what I mean in a minute here. So let's say R squared is equal to 0.98. We add a variable, and now our R squared is 0.99. If we look at it as 1 minus R squared, we're going from a value 0.02 to 0.01. 0.98 to 0.99. The unexplained part goes from 0.02 or 2% to 1%. And what this says is we have reduced the unexplained part by 1/2. And that is a large improvement. We've cut the unexplained bit in half. Now, let's take another example. Let's say we start with an R squared of 0.48, add a new variable, and we have a new R squared of 0.49. So R squared in each case has gone up by 0.01. But if we look at it from the unexplained viewpoint, we're going from 0.52 to 0.51. And we have reduced the unexplained part by 1/50th. Not a large improvement. So this is a useful, more useful way of looking at the impact of new variables on your R squared, and helps you decide whether or not that new variable is worth including in your model, considering that the more variables you add to your model, the less simple, the more complex the model becomes and the less, in many cases, the less useful the model is to explain what's going on. When you've got 50 different variables, they might have great R squared, but each one is only contributing a little bit to the insight that the model gives you. Any questions on R squared? I see we've lost most everybody here. That's okay. I think they'll come back and look at a recording at some point. It's going to be a long session tonight, so I've got a lot to cover. Let's talk about F statistics a little bit. The partial F is one of our most important measures, and this explains the significance of a single variable. So one variable out of many in a multiple regression model. And then we have the whole model F-stat or F-test. And this is testing the significance of the entire model as a whole. Whether any variable or any combination has significance. So should we throw the whole model out or keep it? For a single regression model, you should find that F equals T squared. So you want to test for F being greater than or equal to 4. For a multiple regression, it's not quite so simple. Use the p-stat. Again, 0.05 is your normal cutoff point. Just to give you a little bit of insight into this, the whole model or the whole F-stat is basically calculated as the mean squared model divided by the mean squared error. So the regression model, how much of the variation is explained by that, divided by the mean square, the variation of the error term. And of course, you can go back to that table and see those numbers and calculate that yourself if you want. The partial is a little more complicated. It's done by pulling out individual variables and looking at the impact. And you don't need to know this, but it's the sum of the squared errors of the reduced model, that is the model without that variable, minus the sum of the squared errors of the full model, divided by m. Tell you what m is in a minute. Divided by the sum of the squared errors of the full model, divided by n minus k minus 1. And m is the number of parameters eliminated. Typically 1. A little different for a categorical. N is the sample size. And k is the number of x variables that you're predicting or extracting. You don't need to know that stuff, especially for the final. Just know that the partial F statistic is telling you about the significance of a single variable. It's really useful if you have a categorical, because the T-stat for each level of the categorical is not a good indication of whether that variable should be included or not, because you can't include part of a categorical variable. So you have to look at the F test for the partial F test for the whole categorical variable. And if you're looking at the model overall, is my model of any use whatsoever, look at the whole model F stat or F test to see whether the model as a whole has any usefulness. Next thing we have to worry about is collinearity. Remember, collinearity is caused by correlation between predictor or explanatory variables. And essentially, it's when you've got two variables that kind of move together. It's almost like saying you don't have as much information. When you combine the variables together, they don't add as much information as two independent variables would have. And you can think of it as the impact is kind of like reducing n, the sample size. And remember, standard error is proportional to 1 over the square root of n. So we would adjust for collinearity. And the adjustment we make is something called VIF, the variance inflation factor. It's basically how much the standard error is of a coefficient is enlarged due to collinearity. And of course, if you have a larger standard error, it means that that the confidence interval for the coefficient of that variable is wider. So how much the standard error of a coefficient is enlarged due to collinearity. So you have a new calculation. Remember, we start with RMSE, scale it by n, and then multiply by this factor that's dependent upon the spread of x, and then we add or multiply by this third factor, square root of the variance inflation factor, and VIF has a range of 1 to infinity. 1 is where there's no collinearity, and if you want to understand how this is calculated, it's simply comes from the covariance between the two x values. And it's more complex for greater than two correlated variables. So what do we do? What to do about it? First one is suffer. Leave it in and ignore the fact that you've got collinearity. The model is still valid. The fact that two variables are kind of moving together and contributing the same information to your prediction is okay. And it's okay if that's what you're using the model for. So if you just want to take, forecast values of the x variables and plug them into the model and see what the response would be, it still works. The model is completely valid as long as, of course, you've checked the partial F and all that sort of stuff. Second, you can transform or combine. Is there a way that you can combine the two variables into one measure or something like that, so that the impact of both is included in a single variable? Or you can throw one of them out. So if they both are giving you the same kind of information, throw one of them out and let the other one handle the full load. Okay, collinearity, you'll probably get one question on the exam for that. And now let's look at some of the analytical tools that JMP will give you before we start applying some of this stuff. Let's look at the residual plot, probably one of the most important plots that you'll want to use. And what we're doing is we're taking the regression and we're pulling out what the regression line itself would predict, and we're going to compare the residuals only. We're going to look at the residuals without the impact of the regression line. So we're going to take the regression and essentially subtract it out from all of our data points. And so the regression line would be a horizontal line in the middle. And so we're going to plot essentially all of the residuals, plus or minus, above or below that regression line. And because we have a multiple model, we're not going to use an x variable here. We're going to use the predicted y value. So we might have 5 x variables contributing to a single y value. For every y value we have, we're going to plot along the x-axis y and the residual, the error above or below that regression line. And so we'll get a bunch of dots. And so basically the distance from the regression line equals the residual value. And so this is a very useful plot, especially for multiple regression, because otherwise you'd have to be looking at a regression line that compared each individual x. So you had multiple graphs, each individual x, and look at the residuals above and below that line. And that will only give you part of the information you need to know. And so this plot is really, really useful. If you're looking for heteroscedasticity, for example, you will now see in a multiple regression model whether the variance of these residuals is the same, is constant. Pulling out the regression line, the influence of all of the x variables, let's look at what the error left over is, and that's what this is plotting directly. The next one that we might want to look at, before I go there, this would be, for example, as I mentioned, a useful tool for looking at something like non-constant variance. So this is an example of heteroscedasticity. Where you can see at one point along the y-axis, the RMSE is smaller, and at another point further along, the RMSE is bigger, so it's non-constant. So this is a good diagnostic for seeing if you can then use RMSE and all of that stuff and rely on standard errors of the slope and all that sort of thing. Next one, whole model leverage. So we're going to plot predicted y versus the actual y value. And this 45-degree line here, which serves as kind of the center, is where the predicted y is the same as the actual y. So if you had an ideal regression, you'd have points that were just along that line. But in the real world, we've got points above and below that line, showing us that we have some residuals. And jump even gives us a nice confidence interval. They go to great lengths to calculate it, so we might have a little bit of curvature there. And so this is helpful to look if you've got single values in your data set, your sample, that might have strong leverage on your prediction line. So of course, if you've got a multiple regression model, it's kind of hard to do a single X regression, single X leverage plot. So this is a whole model version of that leverage plot. It allows us to see if there are particular data observations, data values that have extraordinary leverage on our model as a whole. We can also look at the single effect leverage. And this one is a little bit different. Essentially, we're going to take and plot the X leverage for a particular X. And we're going to look at the residuals in Y. And the center line, the flat line, is if X is not included in the model, what is the impact of this particular X variable on Y? None, 0. And then the slope is just the slope of the actual plot here is the X effect of this one X variable. And what we have here when we look at a particular dot, a particular data value, this distance is the residual value for the full model. And the distance to the flat line is the residual value for the model without X. A single X. Okay. So this allows you to see the look at particular data points and see if they have an impact on any one of the predictor variables, the explanatory variables. Any questions? I think we've covered all of the topics that fill out the whole class to this point. And now we are ready. We're ready to go in and look at some sample exam problems. So let's look at sample exam number 3. Let's see. Start with some easy ones, right? Very first question. Collinearity does not occur in a regression model when? How about all the VIFs are 1? So collinearity, of course, is when two or more